Hey everyone, let's see, last time we learned a technique for studying the rational roots of polynomials with coefficients in z, right? That was called the rational root test. This next result, this is useful when studying polynomials in zp bracket x. So let's say it like this. This next result is useful when studying elements of zp, where p is prime, bracket x, right? So studying polynomials whose coefficients come from zp. And what we will see is that this result, or that studying elements of zp bracket x, is actually useful in studying polynomials whose coefficients come from the rational numbers. So I'll just put this in parentheses, which is important to the study of q bracket x. So we will see that later on. So somehow knowing the nature of roots in zp bracket x helps us understand factorization in q of polynomials in q bracket x. Now, and one thing to point out is that in the book, this result that I'm about to do actually appears in chapter 20. Even though we're in chapter 22, it just made more sense for us for me to lump it into, or to move it into this chapter. So it's found, this result is in chapter 20 of the text. For the most part, I don't do this too often where I take a theorem and move it to a different chapter. But for us, since we didn't even cover chapter 20, but we need this result, I had to put it somewhere. And this seemed like the most natural spot to put it. Okay, so this is going to be theorem 22.6. And this theorem has a name. It's called Fermat's little theorem. And so it goes like this. If we have, let's say we have an integer, call it little a. So if a is an integer and p is a prime that does not divide a, right? So such that p does not divide a, then, and you probably, if you take number theory, I imagine you've probably seen this, a to the p minus 1 is congruent to 1 mod p. So it's kind of a famous result. Obviously, it's named after Fermat. You typically use this or see this in number theory, and it's going to be useful for us also, right? Because we're going to want to study polynomials and the roots of polynomials in zp bracket x. So let's prove this. And so what I want to do is I want to apply the division algorithm. So by the division algorithm, a is equal to, let's use a pq plus r, where, okay, so how does this work? Let's see, the division algorithm says that the remainder has to be between 0 and p, but in this case, and strictly less than p, right? So between 0, including 0, but strictly less than p. But we assumed here that p does not divide a, which means that r cannot be equal to 0. So that means that that r is 1, 2, 3, or could be in the range 1, 2, 3, up to p minus 1. And we can say that like this, where r is in zp star. Right? Right, remember zp star, that means remove 0 from the set. Now, what we know, right, so p is prime, which means zp is a field, which means that every non-zero element ZP is a unit, and so this right here is actually a group under multiplication. Let's say note that ZP star is a group under multiplication. Why did I run out of room there? Under multiplication. Okay, so what? So now what we have. I need to write this carefully. A mod P. That's equal to R. And so, oh, right. So, A to the P minus 1 mod P is equal to R to the P minus 1. All I'm doing is raising both sides of this equation to the P minus 1. So A to the P minus 1 mod P is equal to R to the P minus 1. But what's the order of this group right here? It is P minus 1. Any element raised to the order of the group is equal to the identity. And so what we get is what? So that's a nice slick proof of this result, right? And it uses the fact that ZP star is a group under multiplication. As a quick corollary, so this would be corollary 22.7. So if A is an integer and P is prime, then A to the P is congruent to A mod P. And the proof is kind of just a straightforward computation. So let's see. Remember, in the statement of Fermat's little theorem, what we require is that P cannot divide A. In this corollary, we don't have that restriction. So we're just going to consider the two cases separately. So if P divides A, then what? A is congruent to 0 mod P. And so A to the P is congruent to 0 mod P, which is congruent to A mod P. And so then, you can say otherwise, so if P does not divide A, then we have A to the P minus 1 is congruent to 1 mod P by our previous theorem. All right, so that's just Fermat's little theorem. And so then I can multiply both sides of this congruence by A. So thus, A to the P congruent to A mod P. One thing to point out, so in the literature, sometimes this corollary is referred to as Fermat's little theorem. So just be aware, sometimes what I call Fermat's little theorem is called Fermat's little theorem. In other cases, people refer to this statement right here as Fermat's little theorem. Let me maybe say this. So note, sometimes corollary 22.7 is referred to as Fermat's little theorem. So just be aware of that. Now, as an application, find the zeros in Z5 of the polynomial, so it's going to be, call it f of x, equal to, and it's going to be x to the 101 plus 2x to the 30 plus x squared plus 4. So we're viewing this polynomial as living in Z5 bracket x, and we'd like to identify the zeros of that polynomial. So what do we need to do? We need to go through each of the elements of Z5 and plug them into this polynomial and see if we get 0 or not. Well, okay, so f of 0, that's equal to 4, right, which is obviously not equal to 0. F of 1, that's equal to 1 plus 2 plus 1 plus 4. That's equal to, what do I got here, 8, which is 3. All right, so that's not equal to 0. So 0 and 1 are not zeros. And now, and here's why we like Fermat's little theorem. It allows us to raise elements to high powers very quickly when we're working mod p. All right, so in this case, we're going to be working mod 5. And so when I plug 2 in, I'm going to have to deal with 2 raised to the 101. And 2 raised to the 30, Fermat's little theorem is going to help us do that computation. So f of 2, that's going to be 2 to the 101 plus, well, it's going to be, it's actually going to be 2 to the 31 plus 2 squared plus 4, which I then want to write as 2 times 2 to the 4th raised to the 25 plus 2 cubed times 2 to the 4th raised to the, so that's 3, and then to the 7th. Plus, well, let's just say plus 8 for now. And then what do we know according to Fermat's little theorem? What do we know about 2 to the 4th? Well, 2 to the 4th is equal to 1. Right? So this is going to be 2 plus 8 plus 8, which is 16, 18 mod 5 is 3. All right, so once again, we get non-zero. So that's the point. What I want to do is use Fermat's little theorem, which means since we're working mod 5, every time I get 2 raised to the 4th, I know that's equal to 1. All right? And so inside here, that was equal to 1. 1 to the 25th is 1. Here, there's a 1 right there. 1 to the 7th is also 1. Right? And so that allowed me to reduce things very quickly and figure out what we have. Okay, now for 3, so we have f of 3 is equal to, oh, I erased my polynomial over there. What was it? X to the 100 plus 2x to the 2x to the 30 plus x squared plus 4. As you might be able to tell, I made an arithmetic mistake, so I'm redoing starting at f of 3. So let's see, what do we get? 3 to the 101 plus 2 times 3 to the 30th plus 3 squared plus 4. Okay, so now what I'm looking for, I want to look for powers of 4. Right, so this is going to be 3 times 3 to the 4th raised to the 25th. Then we're going to have 2 times 3 squared times 3 to the 4th raised to the 7th. And then this will be a 9 plus 4. So that's going to be 3. This becomes 1. This will be 2 times 3 squared. That part becomes 1. And then we have plus 9 plus 4. That's going to be 3 plus 18 plus 9 plus 4. So that's 21, 30, 34. Right? Mod 5 gives us 4. So that one's not 0. And then let's do one more. Well, we need to do one more. F of 4. So that's going to be 4 to the 101 plus 2 times 4 to the 30th plus 4 squared plus 4. So that will be, so we're just going to do the same thing here. 4 times 4 raised to the 4 to the 4th to the 25th plus 2 times 4 squared times 4 to the 4th to the 7th plus 9 plus 4. That will give us 4 plus 32 plus 9. Did I do that right? 16 times 2. Yeah, plus 9 plus 4. 36, 45, 49. So that's equal to 4, which once again is not equal to 0. So, wait, why did I get, I don't know, hopefully I did my arithmetic correctly here. Let's check this. 4, 36, how did I get 9? Wait. Oh yeah, so that's 16, 32, and then 9 and 4. So that's 36 plus 9 is 45, 49. You know, it's nice when I'm in person, I always make arithmetic mistakes, or I make quite a few arithmetic mistakes. It's so nice to have students who can actually help me check my arithmetic. But I think I did all this correctly. So what did we find? This polynomial has no roots, or no zeros in Z in Z5. So the whole point for Mott's little theorem allows us to compute high powers of numbers if we're reducing mod of prime. Okay, and so that's the end of chapter 22, and I want to get started on chapter 23. This is maybe this is where the excitement really gets started for this class, right? So factorization in f bracket x. So that's what we're going to be talking about now, is polynomials where the coefficients come from a field. So here's our sort of starting point. So let's let f, what do I want to start with? Yeah, let's let f be a subfield of E and alpha be an element of E. And I want a polynomial in f bracket x. Right? So that's going to be kind of our standard setup here. F subfield of E. Now, suppose there exist a couple of polynomials, g of x and h of x in f bracket x, such that f of x is equal to g of x times h of x. In other words, suppose that we can factor f of x as a product of those two. Now, if f of alpha is equal to 0, then we have zero equals, well, that equals f of alpha, which is phi sub alpha of f of x. Remember, phi sub alpha, that was our evaluation homomorphism, and now we know it's a homomorphism. So that's equal to phi sub alpha of g of x times h of x. Because this is a homomorphism, this is phi sub alpha of g of x times phi sub alpha of h of x. And so, what does that tell us? Well, since E, this is all happening, remember this is happening in E. Since E is a field, which means it's an integral domain, one of these two pieces has to be 0. Right? So since E is a field, we have phi sub alpha of g of x equals 0, or phi sub alpha of h of x equals 0. One of those two has to be true. And so, yeah, this is really, right, if you want to understand zeros of polynomials, then this observation right here actually gives us the motivation for studying factorization, right? Because if you're trying to find zeros of this polynomial, that reduces to the case of finding zeros of the components, the factors here, right? So we can say it like this. So this motivates the study of factorization in f bracket x. Yeah, okay. Okay, so I want to prove this result now. This result that we're about to prove has a familiar sounding name, right? So this is the first theorem from this chapter, and it's called the division algorithm. And it goes like this, so let's let f be a field. And then I need a couple of polynomials, let's say f of x and g of x in f bracket x, where one of them is non-zero. Let's say I want to use g of x non-zero, where g of x is non-zero. Then there exist unique polynomials, q of x and r of x in f bracket x with where f of x is equal to g of x times q of x plus r of x, and so this should look very familiar. This almost looks like the division algorithm, or looks very similar to the division algorithm that we learned for integers. But right now we have a division algorithm for polynomials. Now remember, with the division algorithm for integers, there's this condition on the remainder. The remainder, right, has to be between, when you divide by m, it has to be between 0 and m minus 1 inclusive. Well, okay, so now we need a notion of betweenness, right? But what does it mean for one polynomial to be between a couple of other polynomials? Well, that's not clear. So instead of saying that the polynomial itself is between some polynomials, that doesn't even make sense. Our notion of betweenness comes from the degree. So we can say, and, I need to finish my sentence here. I guess let me put it down here. And the degree of r of x is strictly less than the degree of g of x. Okay, so we need to prove this. And we're going to consider a couple of cases. So, first case, let's look at the degree. So if the degree of f of x is strictly less than the degree of g of x, then here's how it goes. I just need to write this down. Yeah. F of x is equal to 0 times g of x plus f of x. Right? And since the degree, this then plays the role of r of x, so the degree is strictly smaller. All right, so there's the easy case. So otherwise, I want to write out the polynomial f of x. Let's use coefficients. So otherwise, write f of x equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a1x plus a0. And I guess I need to write g of x out also. So, and g of x is equal to b sub m. Yeah, so b sub m x to the m plus dot 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 plus b0, where I want the degree of f to be n, the degree of g to be m. So where a sub n and b sub m not equal to 0. So notice now, since we said otherwise, what we're assuming is that the degree of f of x is greater than or equal to the degree of g of x. And so that tells us that n is greater than or equal to m. Right, so note that n is greater than or equal to m. So now what we're going to do is we're going to work by induction. So we proceed by induction on little n. So notice what we're doing is we're inducting on the degree of f of x. So if, okay, so we start off with n equals 0. So if n equals 0, that would mean that f of x is a constant polynomial, and that forces g of x to be a constant polynomial also. So if n equals 0, then what's it going to be? F of x. Yeah, so that would mean that f of x is just a constant polynomial a0, and g of x is also a constant polynomial, say b0. So we have a0 is equal to B0 times Q plus, say, R. Do I want to use R0? Oh, no, sorry, plus 0. What? Wait, whoa. Sorry, I did something crazy there. So A0 is equal to A0 times B0 inverse. Sorry, I got a little out of control there. Times B0 plus 0. So this right here, that's my Q of x, and that right there is my R of x. Okay, so there's our base case. And so now, let's fix n strictly greater than 0 and assume that this result holds. So assume the result holds. For all polynomials of degree less than n, so all polynomials of degree strictly less than n. Okay, so now I'm going to define a polynomial. So let's define, let's call it f sub 1. So f sub 1 of x is equal to f of x minus a sub n b sub m inverse times x to the n minus m, x to the n minus m times g of x. All right, what just happened here? Well, okay, so let's explain what just happened. What are we doing here? So let's look at, remember, g of x looks like this. It looks like b0 x to the m plus dot 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 plus, not b0, sorry, bm x to the m plus dot 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 b0. So if I multiply by this term right here, what happens? All right, so an bm inverse times x to the n minus m times g of x is going to be the polynomial. So let's see now, its coefficient, its first coefficient is going to be a sub n x to the n. Also remember that f of x, right, you don't need to write this down, you already have this, but I erased it, so I just want you to see what's happening here. F of x is a sub n x to the n plus blah, 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 blah. So if I subtract f of x minus this polynomial right here, what happens? Well, the leading term gets killed, which means that this polynomial right here has degree strictly less than f. Right? Its degree is smaller than the degree of f, which means that it's strictly less than n, and that's going to allow us to apply our inductive hypothesis. Right? Right, so that's the point, is this is just sort of rigged to make it work. We need to cook up a polynomial whose degree is strictly less than n. This does it. And notice right here, well, and also right here, we needed to be working over a field, right? For the division algorithm to work, notice that we're working in f bracket x, and here's the reason. To get a division algorithm, right, we need to be able to take inverses, and so there it is right there, right? We can write raised to the minus 1. We have inverses as long as we're working in a field. Okay, so then the degree of f1 of x is strictly less than n. And so we can apply, the division algorithm holds, and so that means that f1 of x is equal to, what am I going to use here? G of x times, say, q1 of x plus r1 of x, where the degree of r1 of x is strictly less than the degree of g of x. So now, remember what we're trying to do. We want to apply, or we want to show that we can run the division algorithm on f1. So we want to, on f. We want to express f as g times q plus r. So now, f of x, let's see, f of x, if I solve in this equation right here, right, f of x is equal to f1 of x plus an bm inverse x to the n minus m times g of x. I'm going to substitute in place of f1. So this is equal to g of x times q1 of x plus r1 of x plus this stuff here, so an bm inverse x to the n minus m times g of x. Okay, so now I want to factor the g of x out of all of these pieces here. So I'm going to continue on with my equal sign, right? So this equal sign belongs right below this one here, right? So I'm going to factor out the g of x. And then we're going to have q1 of x plus r1 of x. Oh. Right, yeah, okay, so, no, I don't want the r1 of x there, that's outside, plus an bm inverse x to the n minus 1, oh, no, n minus m. Make sure I got this right now. G, pull the g's out. Yes, okay, and then plus r1 of x. Now, we know that the degree of r1 is strictly less than the degree of g. And so, let's say setting q of x equal to q1 of x plus an bm minus 1 x to the n minus m, and r of x equal to r1 of x, we have result. Okay, so now what we've shown is that anytime if we have polynomials f and g, where g of x is non-zero, then we can express f of x as g of x times q of x plus a remainder r of x, where the degree of r of x is strictly less than the degree of g of x. Now, we're not done with the proof. We still need uniqueness. All right, what we've shown is existence so far. And I kind of would like to say have the result by induction. Okay, so now let's complete the uniqueness portion. So suppose we have a couple of different ways of expressing f of x. So suppose f of x equals g of x, q of x plus r of x, and f of x equals g of x times, let's call it q bar of x plus r bar of x, where r of degree of r of x and the degree of r bar of x, right, are strictly less than the degree of g of x. Okay, so now we know that these are equal to each other, right? So then we have, so let's say g of x times q of x minus q bar of x is equal to r bar of x minus r of x. Okay. Now, how is this possible? Well, let's think about what's happening here. In an integral domain, when you multiply polynomials, right, if they are non-zero polynomials, then the degree cannot go down. So on this side, we have a certain degree, and the degree over here is strictly smaller than the degree here. So let's say, note that the degree of, I'm going to be a little bit sloppy here, the degree of the left-hand side is strictly greater than the degree, yeah, be a little bit careful here. So note that if, right, okay. Note that the degree of the left-hand side is strictly greater than the degree of the right-hand side, unless both sides are 0. So unless r bar of x is equal to r of x and q of x is equal to q bar of x, right? So the only way for this equation to make sense is if we have 0 on both sides. Since g of x is non-zero and we're in an integral domain, that forces this part to be 0. So each of these polynomials, the q is equal to q bar and r is equal to r bar. Okay, so that completes the proof, and I think that's enough for now. This proof is one that shows up on final exams. It shows up on midterms. It shows up on qualifying exams. This is one that you need to know. Okay, so hopefully you enjoyed this, and we will see you next time.